Okay, so day 2 of the growth and decay differential equations. Growth and decay differential equations. Again, we've done plenty of differential equations. We even did some growth and decay ones. We just didn't call them that at the time. Yesterday we did 1 through 7. Today we'll just do 8 and 9, and then we'll do a couple off of the actual worksheet. So number 8, the half-life of Pu. Was that polonium maybe? Anyone? Chemistry? Is it polonium? Or is it plutonium? Oh, it tells me right there, plutonium. There we go. Thank you. Half-life of plutonium is 24,000 years. Let's pause there for a minute. Do you remember what half-life means from chemistry or anywhere else? Like it's the word itself is describing what's going on. Half-life is how long it takes to get half of whatever you started with. So that means after 24,000 years, you'll have half of whatever you started with. That's what half-life means. 10 grams of plutonium isotope was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? Okay, so that's got to be cut in half several times. So it will take several 24,000 year periods to get there. All right, so even before I'm starting this problem, if I started with 10, to get to 5 would be 24,000 years, and then to get to 2.5 would be another 24,000 years, and then to get to 1.125 would be another, no, not 125, 1.25, another 24,000 years. So 24, 24, 24. So that's 72. So at least 72,000 years before that 10 grams gets all the way down to 1 gram. So even before I do the math on this, I can have an idea of where I'm headed. It's estimated that 1 gram of that inhaled dust can give cancer to 5,000 people. So we've got 72,000 years of some cancer-causing agent floating in the air around Chernobyl. If this problem is accurate, I don't know if it is or not. Okay, so let's see, half-life. We started with 10. Yeah, let's make that table of values. So let's go T, and we could use P for plutonium, or A for amount. I think I'm going to go A for amount. So at T equals 0, there were 10 grams. And we want to know what happens, or how long it takes. So we're looking for time. We probably won't fit in that box because it's more than 72,000. But time to get to 1 gram of plutonium. Okay. There's a couple ways to work this problem. One way fits all the other, matches the equations, match all the other ones. So that makes it easier in that sense. But the other way is using this idea of half-life. Whatever our starting amount is, we're going to multiply by a half however many times. So time over 24,110. If you understand where this comes from, this is a whole lot easier. You don't have to do any calculus. Like, that's the answer. Now let's see if this makes sense. This is what we started with. That's probably the easy part. 1/2, because we're cutting it in half. But do you understand this exponent? T over 24,110. Okay, a few yeses, a few nos. The exponent is how many times I'll multiply by a half. Right? Like, whatever the exponent is how many times I multiply by a half. Well, for every 24,000 years, I need to multiply by a half. So if T is 24,110, then I'm multiplying by a half. That makes sense. If T is 48,220, well, then I'm multiplying by a half twice. But that's right, because in 48,000 years, we should cut it in half twice. So, because we'd say A0, times 1/2 to T over H, where H is the half-life. To me, I would just use that formula. Otherwise, you got to find K and you got to do calculus. It's like, it's just a whole lot easier if you can understand this formula. Okay, so if we're good with that formula, then all we got to do is plug in 1 for A and figure out what T is. So now this isn't a calculus problem at all, it's an algebra problem. So we want to get that T out of there. Let's divide by 10. And then what do you want to do next? What's the next step? How do I get that T out of the exponent? Let's natural log both sides. So natural log of 1/10 equals natural log of 1/2 to the T over 24,110. And again, the reason we did that is we can bring that exponent down front as a coefficient. Again, there's no calculus in this problem at all. So let's multiply by 24,110 and divide by natural log of 1/2. So 24,110 times natural log of 1/10 divided by natural log of 1/2. This would definitely be a calculator problem. Maybe one where you want to use the fraction bar thing to make sure it's clear who's where. So 24,110 natural log 1/10 over natural log 1/2. And remember, my answer was, I'm pretty sure it's more than 72,000 because it took 3 cut in halves to get it to 1.25, and I need to get it a little bit lower than that. So let's see, 80,000. So I'd believe that. So 80,000, 91, 3 decimal places. So it's a little overkill with 3 decimal places. I can't imagine this model would be that accurate. Plus, it's 80,000 years from now, so who's gonna be around to check? But if it doesn't say, always do 3 decimal places. Now that one, I guess it gets the stamp because it wasn't even calculus. It was just an algebra question. If we understand and can use that half-life formula. The other way to work the problem is to say, well, T is 1, or no, not after 1. That'd have to be 24,110. You don't want, it just takes too long to do that. If you understand the algebra of the problem, it's not even a calculus problem because of the half-life thing. All right, number 9. 9 is definitely a calculus problem, and it's not frequently, but it does show up on the AP test, Newton's law of cooling. The good news is that they always tell you what it is. So there's a set formula, but they always give you the formula in words, and so it's one where if you can translate what it's saying, it gives you the formula. You just have to know what to do with it after it gives it to you. Newton's law of cooling states that the rate of change in the temperature of an object, so that sounds like, you tell me, what does that sound like variable-wise? Rate of change of temperature. a derivative. What do you want to use for temperature? You can use T, just be careful because time is in there as well. So, what's that? F for Fahrenheit? Okay, that works. Some people use uppercase T and lowercase t, but then it's like, you better be careful about which T you're dealing with. And so a lot of books use different things. I've not seen F, but I like F because that sort of reminds you that it's Fahrenheit. So we'll say F is temperature in Fahrenheit, and little t will be time. So rate of change in the temperature of an object, so we'll say that's dF dt, is proportional to, so equals K times the difference between the temperature of the object, that's the F thing, and the temperature of the surrounding medium. Okay, so that's like F minus whatever the temperature of the medium is. We don't know what that is. I think they're about to give it to us. So that's Newton's law of cooling. We use it a lot, but every time we use it, we tell you what it is. So you don't have to memorize the formula. You have to be able to read the words and come up with the formula. Suppose that a roast turkey is taken from an oven when its temperature has reached 185 degrees F and is placed on a table in a room where the temperature is 75 degrees Fahrenheit. If the temperature of the turkey is 150 degrees after half an hour, what is the temperature after 45 minutes? Okay, that's a lot of information. So T, so F is our turkey temperature as opposed to room temperature. So let's see. It's 150 after half an hour. Although here we've got minutes, so I'm going to switch to minutes. After 30 minutes, it's 150, and what we want to know is temperature after 45. But what else do I know? What did I leave out of my table here? What is the temperature at 0? Good, 185. The temperature of the turkey is 185 when we take it out of the oven. Well, where's this 75 go? What's that talking about? Room temperature is 75. That's the surrounding medium. So that 75 is what goes there. That's a constant. So we don't have to worry about that as a variable. That's a constant 75. Okay, so I've got an equation. So I'll have to separate and integrate. I've got some information, especially two pieces, so that will help me figure out what K is, and when I integrate, C will show up. So that'll help me there. And then once I get it all solved out, I'll have to just plug in 45 to figure out what the answer is. Okay, so separate. Let's see, dF over F minus 75 equals K dt. Separate, then integrate. And now we get to see who knows how to integrate. Oh, Addie wasn't here yesterday, so that would be cruel. But I have faith in Alan and Tyler. Tyler, I feel like you got the easy one, so we put Alan on the spot here. Natural log, okay? So you can do a U substitution if you want, but hopefully you've seen that enough to know that that's natural log of F minus 75. A quick word on the absolute value bars. You know, it's supposed to always be there, but if we think about what's going on in this problem, the turkey is taken out of the oven at 185. The room temperature is 75. So F's always going to be bigger than 75. So I don't have to worry about the absolute value bars, because the temperature of the turkey is not going to dip below the temperature of the room, right? That'd be kind of wild. That would violate all sorts of science laws if it got colder than the room it was sitting in. So officially, mathematically, I need the absolute value bars, but it's not going to matter for this problem because we're not going to go below the temperature of the room. Tyler, how about the other side? KT plus C. Kira, do you know what we want to do next? So you're on the right track. I want to undo that natural log. So I want to E both sides, or fish hook it. You could phrase that either way. She was saying E both sides, so I'll write it like that. But that's the same thing if you do the fish hook. And the reason you do the E to both sides, because E and natural log cancel each other out. And then on the other side, E to the KT plus C. Grenier, there's some algebra magic going on the right-hand side here. What can I do with this? I mean, eventually I'm going to plug in 0, and that's going to make things nicer. But before I do that, I can put that C down front. I mean, be careful. It's because it's not the same C. It's a different C. Because remember, this is E to the KT times E to the C. And then this E to the C is where that C comes from. And we may as well solve for F because we're almost there. So 75 plus C E to the KT. Okay. Calculus is over. Now it's algebra time. Let's plug it in that first point. So 185 goes in for F. And 0 goes in for T. And what's E to the 0? 1. So 185 equals 75 plus C. So C is 110. So back up here to the top. So F equals 75 plus 110 E to the KT. And maybe this is starting to make sense. Now if time is 0, 75 plus 110 is 185. So that matches up on our first point. Now let's do our second point here. So F is now 150. And I opted to do this problem in minutes. You can do it in minutes or hours. Just make sure you pick the same thing. So either 30 and 45 or 1/2 and 3/4, either one. But I think minutes is easier, so I'm going to use minutes. All right, more algebra. So subtract the 75 and then divide by 110. And then we've done this a bunch now. What do we want to do next to start to get K by itself? Natural log both sides. So natural log 75 over 110 equals 30K, because natural log of E is 1. So K equals natural log 75 over 110 divided by 30. And that looks crazy, so that's probably going to be stored in my calculator as K. That way I don't have to worry about it anymore. Natural log 75 divided by 110 divided by 30. Store that as K, and then I'm done dealing with K. I mean, if you want to write it down, just, I don't know, you don't even need to write it down. If your calculator knows it, then you're good. Okay, so between that statement and there's what K is, like those two things, now my problem is defined. Like I'm done. Now I just need to answer the question. So let's plug in 45 for our final step here. And this will be a calculator thing for sure. 75 plus 110 e to the k times 45. And e is just a number, k is just a number. Your calculator always knows what e is. And you just told your calculator what k is. So all I have to do now is type all that in the calculator. 75 plus 110 e to the 45k. Oh, I forgot to do the guess thing. Like when we lay it out like this, any guesses on what this number will be? Let's see who's a good guesser. 138. Okay. 138. I like that guess. It's definitely lower than 150. Right? And it's definitely above 75. So like, even though this problem is hard because there's tons of information, the more information there is, the better you can sort of guess what the answer is going to be. In fact, if we let the t go forever, then eventually this thing is going to be at 75. So I know it's got to be between 150 and 75. It's only been 15 minutes from 150, so 138 sounds like a good enough guess for me. We'll find out if Tyler has already typed this in the calculator or if he was legitimately guessing. 137. Yeah, good work. So 136.929. Again, 3 decimals because that's what you're supposed to do. But could you even really measure temperature to the third digit of Fahrenheit? Kind of doubt it, but so good guess. But that's I almost said beauty. That's a little bit of a stretch. That's the nice part about a word problem is you can know if your answer makes sense, right? If I got anything above 150, I would be very suspicious. Anything below 75, I know is out. And so that's a pretty narrow, like of all the numbers in the world, I know my answer's got to be between 75 and 150. And so when you get one that's in there, you feel pretty good about your answer. So the harder they are, yeah, it takes longer, but the better in terms of if you're paying attention, you can feel good about your answer. I guess that's always the case with word problems. You have some reasonable idea of what your answer should be. All right, so that's a big problem, but Newton's law of cooling is fairly common. Again, they will always give you the setup. They won't give you the formula. They'll give you the words, and then from the words you can get the formula and kind of go from there. Some books, and I guess maybe some teachers, you can jump to the very end and say, well, it always ends up like this, and memorize what all those pieces are, but it's not worth too much brain power to do that. Just start with what it gives you and go through the calculus. And besides, on the AP test, they'll be looking to give you points for separation of variables. So there's 1 point. And if you integrate both sides and get the constants in the right place, that's probably a point. And then finding the constants, that's probably another point. So show your work. Get all those points in there. Okay, let's look at the worksheet. And let's do number 4 together. because this is sort of like the half-life thing, except a certain bacteria doubles in size every minute. If there are 20 bacteria initially there's 20, and hey, I know it doubles every minute, so I could add some pieces here. After a minute it's at 40, after 2 minutes it's 80, and so on. How long does it take the population to reach 1 million? Okay, well, let's see the amounts. What would be this time? We started with 20. We're multiplying by 2. Not multiplying by half this time because we have a double time. And t over, this one's almost too easy, because every minute it's like t over 1. Usually it's t over whatever the half-life time is, or the double lifetime is. So for every minute we're multiplying by 2. So now this is just an algebra problem. I'm going to plug in 1 million for b and see if I can figure out what t is. In fact, I'm going to pause and let you do that to make sure your algebra is okay. So grab a calculator, and hopefully nobody does 20 times 2 as their first step. 15.61 minutes. That seems really quick to get to 1 million, but you can sort of check this, right? Like, because at 3 minutes you'd have 160, 4 minutes you'd have 320. So, and then each time I hit enter is 1 more minute now. So wait, that was 4. That's 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes, 11, 12, 13, 14, 15, and that's 15 minutes. That's less than the million. So if I go past 15 minutes, I'm over 1 million. So you can, sort of check your answer. You couldn't get it exactly doing that, but you could get it kind of close. All right, so your job is to finish worksheet 3. Most of them, maybe not even most of them, a chunk of them are sort of work them out problems, but then you get to number 9. Let's actually look at number 9. A bunch of them are like set up the problem, so you don't really have to do anything. I mean, you could argue that's the harder part. Like, you don't have to do the algebra, it's just the calculus. So actually you try number 9, because there's a lot going on in number 9. I'm just going to press pause. Logistic growth, and what it looks like is, initially it looks like exponential growth, but there's a limiting factor. Like, there's only so many people who can hear the rumor. Like, it can't continue like this forever, because there's only so many people in the world, or in the high school, or whatever. And so eventually it sort of flips over and turns into this. And it's been a few years now, but when COVID started, people were modeling the growth of a disease with this kind of curve. Because initially, when there's not many people that have it, it looks like, oh my gosh, everybody's getting this thing. It's just blowing up. It's like, well, that can't continue forever because there's only so many people on the earth, or only so many people in the high school when everyone was, not dropping out, but having to go home for COVID. And eventually it's like, well, we've all got it now, we're just steadied out. But that plan, it would have been interesting to plot the data to see if it followed something like this. But that's logistic growth, and that's a real world growth curve. In fact, it's a real world growth curve when there's a limiting factor. And so, like in nature, like the rabbits can't double forever because eventually they run out of a food supply or something's going on. They're not going to take over the world. And so there's some upper limit to the number of rabbits there are. Or the bacteria that was doubling every minute a minute ago in that problem. Like, they can't double forever. Maybe there could be 1 million bacteria, but eventually the size of the petri dish constrains that growth. And so initially it looks like exponential growth, and eventually it's like, well, there's some limiting factor up there that that prevents us from going beyond that, either the number of people or the size of the petri dish or whatever. So as silly as this problem may have seemed, this might be the most realistic example in here, because that is how growth occurs in nature, where there's some limiting factor. And I mean, there's always some limiting factor, right? You're not rabbits aren't taking over the world. Okay, so that's a good one to do. And again, there's questions like that on the AP test where they can make up something completely random, and you've got to just read carefully. And you didn't even have to do any algebra on that one. That was all set up, and so hopefully, if you could read carefully, you could get kind of a free one. 10 through 14 are all kind of the same thing. Like, read carefully, and you can get the problem. All right, so today's assignment is 1 through 14. Again, we did number 4, we did number 9. 1 through 8 are the longer problems. 9 through 14 is just make them match up.